Thanks, Geo, for the kind introduction, and good afternoon, everyone. I'm Michele. I work in project 2 of TACO with Uli, and our role is, so we want to understand better perovskite oxide surfaces with atomic scale resolution, which typically means with scanning tunneling microscopy. So I would like to give you a little bit of a flavor of what we do, how we do it, and which difficulties we may encounter in doing that, and how we can try to go around these difficulties. So what I will show you is mostly part of the research that we've been doing during the last years, and I would like to give you a feeling of where we're going to go next within TACO. So we're talking about perovskites. I'm sure I don't have to introduce perovskites so much to you. It's a structure based more or less on this cubic-ish unit where one atom type sits at the corner, another atom sits at the bulk, at the body center of the cube, surrounded by a cage of anions, in our case oxygen. The funny thing about perovskites is that you can more or less pick any 3 atoms from the periodic table, mix them up together, and they will have at least an allotrope that has a perovskite structure. And for this reason, they are on the one hand complex, very complex materials, and on the other hand, they are very tunable, meaning you can pick atoms appropriately, and you can induce the properties that you want. So you find insulators, metals, superconductors, multiferroics, whatever you like. And for this reason, perovskites are used, or at least have the potential to be used in several applications that go from electronics all the way to catalysis. And so we're not much interested in the bulk properties of these perovskites, but rather the surfaces, because as you heard, surfaces where these materials interact with the surrounding environment. So we want to understand which surface structures you can have, where each atom sits, and why having one surface structure has an impact on the properties of these materials. And we want to do this with materials that are actually used in applications. The problem is, for us surface scientists, is that these materials look pretty messy, so you cannot really approach your STM tip there and get atomic resolution. So we simplify our life a bit and use what we like to call the surface science approach. That is, we pick one or a few crystal orientations of these crystal lights and rather study single crystals of these same material under those orientations. And we do this under very controlled conditions, typically ultra-high vacuum or very clean conditions. So the advantage here is that we can then approach our tip and get atomically resolved images, and we can interface with our theoretician collaborators. So once you want to do this for perovskites, you encounter immediately a problem that is, except for a few rare occasions, you don't find single crystals. You cannot buy single crystals, so we actually have to build our own samples. And typically we do this by growing single crystalline films of these materials on appropriate substrates. So this is our first step in our work, that is finding a way to grow the right material with the right composition, with the right structure, and that is flat enough so that we can approach our STM tip on. And then once you have these single crystalline films, you can look a bit closely, more closely with your STM, and it turns out that this flexibility that I mentioned for the perovskites becomes a nightmare at the surfaces, because even if you take one single crystal orientation, you have seen this already, strontium titanate, you find a host of different surface structures. And so for us, then, we have to understand how can we control each of these surface structures, how we can pick one or the other surface structure, how we can prepare a sample with one of these surface structure only or the other, and how having one of these surface structure impacts the properties of the material. But before we can actually go and investigate properties that are meaningful, what we really need is structural models for these surface structures. And that's where TACO comes in as a very crucial point, where so essentially we have to try and combine our experimental observation and input from theory and the other way around to try solving the complicated structures that we see on these perovskite oxides. So I don't have time to go through all or what we do in all of these aspects, but I will stick to the first step today, that is about how we grow our samples and how do we get these single crystalline films. So all the experiments that you will see in a minute have been performed in this UHV machine, where you see here in front, here is the growth chamber. We grow by pulse laser deposition. I will come back to it in a second. And this growth chamber is connected in ultra-high vacuum to our surface science lab, where we have scanning tunneling microscopy, low energy electron diffraction for structure and morphology, and X-ray and ion spectroscopy for chemical characterization, and a preparation chamber where we can clean our surfaces. So the way we usually go, we just take a sample from a box, a single crystal, typically strontium titanate, you put it in the chamber, and then you clean the surface a bit, make sure it is well ordered, make sure it has the right surface structure, the one you want, and then that you can do, of course, by checking your surface with all these techniques. And then you move your sample in ultra-high vacuum all the way to your growth chamber. You grow a little bit of material, then you can go back and see what happened. And all of this is done in ultra-high vacuum conditions, so we can avoid contaminations from the atmosphere. Very good. So I mentioned we grow with pulse laser deposition, so let me give you a little bit of details of how this actually works. So you have a target of the material that you want to grow. This would be your film, for example. You have a pulsed ultraviolet laser, and you focus this pulsed ultraviolet laser on the surface of your target. And every single pulse removes a little bit of material, ablates the target. And the material that you have removed then expands in the chamber where that we have filled with some gas, oxygen typically for oxides, and then ends up condensing on your substrate on the other side. So this sounds pretty simple to some extent, but it turns out that if you want to grow nice films, you really have to take care of a few steps in here. So on the one hand, especially when you want to deal with complex materials with multiple components. So on the one hand, the laser can remove one or the other atom more efficiently from your target, what is called incongruent ablation. Then your materials typically have atoms with largely different sizes, so these different atoms can scatter differently with the background gas, and that will lead to a change in the composition. And in the end, you have your substrate where you have surface reconstructions. Things can stick, cannot stick, can stick less, can stick more, can re-evaporate. You can implant stuff. So these are all parameters one has to take into account. All in all, that means that to grow nice films, you have to tweak a bit parameters. And if you don't, or if you actually do not optimize them all the way, what you end up is ugly samples. Meaning, typically, you find boulders on the surfaces, and this is not what we want for our STM investigation. You cannot really approach your tip on something that looks like this. It's a bit of a mess. What I want to tell you is that what we think is that all what you see here is because the parameters were not fully controlled, and the composition of the material that you have been growing was not perfect, and that the surface structure that you have on the substrate or on the film as you grow is extremely relevant in determining the final morphology of your films. So I hope that's enough as an introduction. So I don't go through all the details again. I will stick only to one parameter, which is the pressure of the oxygen gas that you have in the background, and I will be talking about this guy over here, lanthanum strontium manganite films grown on strontium titanate 110 surfaces. So LSMO for friends is a perovskite. Perovskite, we are looking at the 110 orientation, so that would be this plane. And one tricky point with the 110 orientation is that it is polar. This means that if you look at the bulk, basically this is composed of layers with plus charge and minus charge alternately stacked. And this means this looks like stacking many parallel plate capacitors. So as you stack many of these parallel plate capacitors, you have energy associated with these parallel plate capacitors, and if you stack a lot of them, the surface, the electrostatic contribution to surface energy diverge. This essentially means that a bulk truncated surface of one of these samples does not exist, and the material itself compensates for this polarity by changing the composition of the surface. So it changes the composition of the surface such that you have a well-defined formal charge that counteracts this parallel plate capacitor. So it's basically like placing another one the other way around. Very good. And LSMO does this in a variety of ways. I will not go into all of these structures. The one important thing that turns out is that each of these structures is intrinsically related to the composition of the surface, which means that we now know if we have this structure, we want to go here, we now know we have to deposit a little bit of manganese. And here we are around with the A-site cations. Okay, so on the left side here you will have A-site rich reconstructions. On the right side here, B-site rich reconstructions. And this is going to be quite relevant for what I will show you in a second, which, as I mentioned, I will be talking about the effect of the growth pressure on the growth of these films. So starting from the beginning, we can compare some thin films grown at 3 different pressures, lowish pressure on the right, highish pressure on the left. All of them look rather fine from the morphological point of view. We have steps and terraces. This seems quite all right. Turns out that if you look a little bit closer with STM, this guy grown at high pressure has a surface structure that looks like this. This guy has a surface structure that looks like that. So, and in between, something in between. So this looks like at high pressures, we are introducing a bit too much of the A-site cations, and at low pressure, we are introducing a bit too much of the B-site cations. Is this a problem? Doesn't look like, especially for these thin films. They all look nice and flat. Actually, it turns out to be quite of a problem as soon as you start increasing the thicknesses of these films. So you go twice, give or take, twice as thick over here, 5 times as thick over here. You start seeing some clusters forming at the surface. And there's only a sweet spot, let's say, where you can grow very thick films without degrading the morphology. So logically, one would assume then here we introduce a bit too much of the A-site, so this is probably some A-site rich clusters. Here we had a bit too much manganese, so this is B-site rich clusters. So is this true? Well, we can have a look at XPS, and this is actually the case. Here you see manganese intensity over lanthanum intensity, no atomic concentrations at all. But you see up here at the low pressure side, we have quite a lot of manganese. At the high pressure side, quite a lot of lanthanum, so A-site. So what's going on over here is that most likely at the conditions where we were initially growing, at the laser fluence that we were using, we were ablating preferentially manganese, removing preferentially manganese from the target. So that means that at low pressures where everything that you remove goes more or less straight on, you find a lot of manganese at the surface, while at higher pressure, the manganese is much lighter, so it would get scattered more out of the forward direction where your sample is. And you end up with an enrichment of the A-site cations. So all in all, that means that there seems to be some optimal pressure somewhere over here where we can actually grow thick films without degrading the morphology. Now the question is it all random, or can we find this pressure nicely? And it turns out that we can. Luckily, STM turns out to be a very good technique, surprisingly, to do this. So as I mentioned a while ago, we said, okay, surface reconstructions are intrinsically related to composition of the surface. So we can use a little bit of a trick, and we can start from a surface, a certain let's say a thin film with a certain surface reconstruction, then grow a little bit on it and see whether this surface reconstruction changes. For example, let's say 2 minus 2 millibar oxygen. And in this case, you see, okay, 5 nanometers, the surface structure actually changed quite a bit towards the B site reach. So that means, I said before, low pressure, too much B site, so we have to increase a bit the pressure. So we increase the pressure a little bit, and here you have to trust me, that 4 minus 2, again, we see a slight shift of the surface reconstruction towards the B site reach side. So that's still too low a pressure, increase a little bit more. That was too much, okay, we went the other way. So we go somewhere in between, and so on and so forth. Now we can start growing thicker, and then you go, and at the end you can pinpoint an ideal pressure we can grow in one bunch of a very thick film without degrading the morphology. We can even be a bit more quantitative and measure how much the surface reconstruction has changed from one to the other. We know these numbers up here, so we can tell that in this case we were introducing less than 0.1% manganese during the growth of these films. So now I've shown you this for LSMO 110. We've done this already also for strontium titanate 110, and we think that as long as you have a little bit of a feeling for which structures can exist under which conditions at the surface, then you can use this technique pretty much for everything to actually grow nice and atomically flat films. So I told you surface structures of LSMO, they depend on the manganese content. Well, the story is a bit more complicated than that. Turns out they also depend on the oxygen content. So it's not only a one-dimensional phase diagram, but a two-dimensional phase diagram. Luckily, we found a way to take our experimental observations and put these structures into a phase diagram where we can tell now which surface reconstruction is stable where. So what I've been showing you so far, and this stuff was part of Jada's thesis. She has a poster, so if you're interested more in this, you can talk to her later on. So all in all, I think that on the LSMO 110, at least for the growth part and for the controlling of the surface structures, we are at a good stage. Now Eric took over Jada's work, and what he's going to do in TACO is, so first of all, we would like probably to try and go the third direction, so changing also the A site content in this LSMO. First just at the surface, and then perhaps also in the bulk. And we just started now with swapping the crystal orientation and going for 001 oriented LSMO films. And here Michele has some preliminary results in his poster, where you can also discuss with him a bit about the 110 surface structures as well. And then later on in TACO, I think we would also like to swap the B cation, so trying replacing manganese with iron. We hope, at least for the growth, we have at least a handle. We will see how this complicated becomes later on. Very good. So now the big elephant in the room is, okay, we have all this bunch of surface structures. How do we go on from there? And I told you we need structural models for these surface structures, and here TACO is going to be very critical. So what has been done so far in surface science, you start from a typically scanning tunnel microscopy image, then one way or the other you come up with a model and you ask yourself, are these two the same thing? And the only thing you can do so far, I think, what people have done is simulate an STM image, look at the experiment in STM and say, okay, I have a blob here, blob there, blob here, blob there. Yeah, perhaps it's right. So, of course, the problem with this approach is that it is, okay, there's other details, but the main problem is that this is qualitative. So you cannot really say, okay, this model is right, is wrong, or perhaps you cannot tell it's wrong, let's say, or you cannot tell how much is wrong. So luckily enough, all our surface scientists have another technique that has been already mentioned, that is low energy electron diffraction. that is underused in all our systems. Essentially, it is more or less at one energy. You can think of it as the Fourier transform of your surface, and it is used typically by just to just check the periodicity of your surface. Turns out that there is actually a lot of information that we are wasting when we do LEED, that is in the intensities of these spots, and it is in the way these intensities change with energy, because these carry information about where each and every single atom sits and what's its chemical nature, what are its vibrations. And it turns out that there is actually a way, starting from a structural model, to calculate exactly the same thing. And there is a number, reliability factor, that you can use to compare directly a structural model with experimental data. A number that tells you 0, yeah, that's perfect. 1, you're completely off, and everything in between. So this LEED IV technique, I think, it's going to be a big part of TACO. We are going to try to develop this LEED IV technique to make it easier to use, because it is very powerful. You see, you have a number that can be then fed back to theory and can be used as a feedback. So the reason why people is not using it is because it's a nightmare to do it from all points of view, from getting good data to extracting the IV curves from your data to actually calculating your curves. And we have been working for the last 2 years together with Lutz Hammer in Erlangen to build Viper LEED and to help people try and do this more often, so that we also have perhaps hopefully in the future a larger use base, more data, and we can improve our understanding of surfaces. So in this respect, we are developing a new hardware, and you can see more details at Flo's poster. Michele came up with some black magic to extract IV curves in seconds, and he's around, so you can talk to him about it. And then Florian has been working in simplifying the interface to the core code that is used for these calculations, and now his work has been taken over by Alex, that started a couple of weeks ago, his PhD. So with this, I'm at the end. I more or less wanted to tell you that perovskite oxide surface is RMS. There's a lot of surface structures. Luckily, we now think we have a handle. We know a bit how to control these surface structures. We understand a bit more this surface structure. We can use this surface structure to grow nice films. But what we are still missing is good models, and here TACO is going to be a huge help for us. We hope that we can build Viper LEED and LEED IV into a bridge between experimental and theoretical approaches. So that's all I have, and well, thanks for listening, and if you have any question, ask.
Yeah, thank you very much, Michele. So are there any questions?
Maybe you hear this more often, but I was wondering if you have this very advanced recipe to make your surface without any oxide clusters on the surface. What would be the recipe that applications use? I mean, usually applications will have, people who go for applications will not have this very elaborated pressure recipe.
Yeah, that is.
So I guess they have more clusters that may have also some functions.
I guess, yeah. I mean, most of the times, in real applications where you actually are not doing fundamental research, typically the approach is more of a trial and error, or a stochastic approach, let's say, where you try a shitload of parameters and then something works and you take that. So I think that's, so yeah, I think for us it is more of a way to control the growth of these materials such that we can narrow down then later the effect of surface structures more easily.
Thank you for the very nice STM pictures. I was wondering if you now have these different manganese concentrations, you see different sort of general patterns, But of course, there's always variation in the, so how much of that information is still contained in your leads when you do different spots?
Yeah. So okay, that's a question that has a theoretical answer, which is all the information is still there, and then a practical question that we still have to tackle is whether we have enough resolution, especially in K-space, meaning the spots become very close together, whether we can still differentiate one spot from the other. And whether, let's say, the number of spots that we have, of beams that we have, is enough for actually then fitting our model to a structure. I think we are currently working on these improvements. I guess Lutz has recently tried with a simpler system, but a very large unit cell. I think it was a platinum 10 by 10 unit cell, and even then it looks like our code so the code can handle these sort of structures. I think there is enough information. So okay, I didn't have the time, but in practice, the amount of information that you have in these data is the number of peaks that you see here. And there's a lot of information if you can acquire a large enough energy range. So I think we can tackle also pretty complicated structures, periodic structures.
Thank you.
Thank you. One more quick question. Maybe while walking down, I'll ask one. So depending on your manganese chemical potential,
yeah,
you already had the results. You were moving from a 2 by 1 to what you called an M by 1. Is there a systematic in terms of these structures? Are they related to one another?
So okay, there is a smooth. Let's say there is a smooth transition that we understand between this guy and that guy. Between this fishbone structure and this 2 by 1, there is a systematic transition. We think these are manganese MnOx overlayers on top of this LSMO, more or less bulk truncated, but it's really more of a guess because these structures have huge unit cells, so it's hard to say, I think. The M by 1 is a bit more of a special case. It's very far off. We cannot really make it as a single phase, so that I wouldn't take as a best example for so it is a different structure, let's say. At least from a phase diagram point of view, it seems there is a miscibility gap somewhere over here where this other structure then appears.
Okay, thank you. So we thank Michele.